Hello and welcome. You found your way to Dreams of Gravity, a place where the cosmos unfolds gently, where stars and worlds reveal themselves not in a rush, but in the quiet rhythm of thought and breath, where time slows and stretches like the space between heartbeats, becoming something you can hold in your mind without grasping, without strain, where knowledge arrives not as a flood overwhelming the senses, but as gentle rain, accumulating slowly over hours, seeping into understanding the way water seeps into soil, nurturing rather than drowning, patient in its persistence, allowing roots to grow deep before new growth appears above the surface. Tonight, I invite you to settle completely into this moment, to let yourself arrive fully here in this quiet space we're creating together, through words and silence and the images they conjure in your mind's eye. If you're able, lie down now. Take your time finding the position that feels most comfortable, most natural to your body at this moment. Perhaps on your back with arms resting softly at your sides, palms open and receptive to whatever comes, fingers uncurled and relaxed, or perhaps curled on your side like a question waiting patiently for an answer, like the curl of a galaxy spiral turning slowly through space over millions of years according to the patient mathematics of gravity, each star following its orbit around the galactic center, each taking hundreds of millions of years to complete one revolution. Timescales so vast that all of human history represents less than 1% of 1% of one galactic year. Let your shoulders drop now, one at a time, if that helps you feel the release more fully, feeling the tension drain away like water flowing downward, following gravity's gentle pull, that same fundamental force that holds galaxies together across millions of light years, that keeps moons circling their planets in the darkness for billions of years, that shaped the solar system from a cloud of gas and dust 4.5 billion years ago, condensing matter into the worlds we see today, concentrating atoms that had been dispersed across light years into dense spheres of rock and ice and gas. Feel the weight of your body being absorbed completely by the surface beneath you, a bed, a couch, the floor. And imagine that weight as a connection, a physical thread linking you to the earth beneath, and through the earth to all the other worlds orbiting our sun, all of us bound by the same fundamental force that has operated unchanged since the universe began. Feel the surface beneath you holding you completely, supporting your weight without judgment or effort, the way gravity itself has held every world since the beginning of time. Matter, as philosophers have long contemplated, cannot exist outside of space and time. These three concepts are fundamentally intertwined, each defining and depending on the others in ways that become clearer the more deeply we examine them. Space is the form of matter at rest, the stage on which matter exists, the distances between objects that allow them to be distinct. Time is the form of matter in motion, the dimension along which change occurs, the flow that carries us from past through present toward future. And matter itself is the substance that gives reality to both space and time. For without matter, there would be no space to measure, no distances to contemplate, no time to mark because nothing would change, nothing would move, nothing would exist to measure duration. Without space and time, matter would have nowhere to exist and no duration in which to persist. They are inseparable, three aspects of a unified reality that we perceive separately, only because of the limitations of our senses and the structure of our consciousness. Close your eyes now if that feels right. If darkness helps you see better, helps you visualize the cosmic scenes we'll explore together. Or let them rest half open if you prefer, gazing at nothing in particular, your vision soft and unfocused, allowing light to enter without demanding anything from it. We have nowhere to be but here, nothing to do but listen and drift and wonder. There are no obligations pressing on you in this space, no tasks waiting to be completed, no emails to answer, no responsibilities demanding your attention. For the next 2 hours, you can simply be, simply exist, simply rest, while your mind wanders through the cosmos. Time moves differently in this space, stretching out like the vast distances between planets, becoming something fluid rather than fixed, something that flows at its own pace regardless of our wishes. The philosopher and visionary Konstantin Tsiolkovsky, who dreamed of space travel decades before it became possible, once wrote that a piece of matter, an atom, a molecule, experiences countless lives separated by enormous intervals of time. Yet subjectively, these merge into one continuous existence. The waiting, he explained, the vast intervals of billions of years between one form and another, exist only for the living who are conscious of time's passage. For matter itself, for the atoms that compose moons and planets and stars, there is no subjective awareness of that flow, no sense of duration, only eternal existence, punctuated by transformations from one form to another. The atom that is part of a rock today was part of a star billions of years ago, and will be part of something else billions of years hence. But it experiences no waiting, no impatience, no sense that time is passing. It simply is, moment by moment, form by form, existing in an eternal now that we, as conscious beings aware of mortality, can barely comprehend. The journey ahead is long in the way a river is long, winding through landscapes it has shaped over millennia, carving canyons grain by grain, depositing sediments layer by layer, patient and unhurried, full of depth and quiet mystery. A river has no destination it hurries toward, no deadline to meet. It simply flows according to gravity and topology, following the path of least resistance, shaping the land even as the land shapes it, existing in dynamic equilibrium between erosion and deposition, between the force of water and the resistance of rock. Tonight, we'll explore the moons of our solar system in this same spirit, not rushing toward conclusions, but allowing understanding to accumulate gradually, each detail adding to the whole, like sediments building up layer by layer over geological time. These moons, those silent companions circling their planets in darkness, are witnesses to billions of years of cosmic history. Each one is a world unto itself, existing in space and time, carrying secrets written in ice and stone and shadow, in the chemistry of their surfaces and the structure of their interiors, in the patterns of craters that record ancient bombardment, and the smooth plains that speak of recent geological activity. There are nearly 900 of them at last count, though the exact number changes as we discover new small moons and as we refine our definitions of what counts as a moon versus a temporary captured asteroid. Each one traces its own path through space according to the mathematics of orbital mechanics, equations first written down by Newton and refined by Einstein, equations that govern motion from the smallest asteroid to the largest galaxy cluster. Each moon exists at a specific location in space at a specific moment in time, and each moment leads inexorably to the next, in an unbroken chain stretching back billions of years to their formation in the early solar system. If we could watch a time-lapse of the solar system's history, speeding up time so that millions of years passed in seconds, we would see the moons tracing intricate spirals through space as their planets orbit the sun, patterns of exquisite mathematical beauty, each moon's motion coupled to its planet's motion, each planet's motion coupled to the sun's journey around the galactic center. Everything moves, everything flows, everything changes, yet the fundamental laws that govern that change remain constant. So breathe now, slowly and deeply. Let the air fill your lungs, as if you're drawing in not just oxygen, but time itself, the breath connecting you to this present moment. Then release it even more slowly, feeling time flow out with the breath, past merging into present, merging into future in one continuous stream. With each breath, feel yourself becoming lighter, as if gravity's hold is loosening slightly, as if you're already beginning to float upward toward the gentle vastness of space, where everything moves according to ancient patterns established at the universe's beginning. Space and time, modern physics tells us, are not separate entities existing independently, but aspects of a single unified space-time continuum, a four-dimensional fabric that curves and flows around massive objects like water, flowing around stones in a stream that expands, carrying galaxies with it like raisins in rising bread dough that was born in the Big Bang 13.8 billion years ago and will continue to exist for incomprehensible durations into the future, perhaps forever if current understanding is correct. What is a moon? The question seems simple on the surface, childlike in its directness, yet, like many simple questions, it opens like a flower into something vast and complex the more deeply we examine it. A moon is a natural satellite, a smaller body bound by gravity to orbit a larger one, held in an embrace that can last billions of years without weakening, existing in space as a physical object with mass and volume and composition, existing in time as an entity with history, stretching back billions of years, and future stretching forward perhaps billions more. Two bodies, one large and one smaller, locked in a gravitational dance that neither can escape, each affecting the other through tidal forces that slightly distort their shapes, each pulling on the other in ways that gradually change their orbits and rotations over millions of years. But that clinical definition feels too cold, too detached, missing the poetry and wonder. Moons are companions in the truest sense, quiet partners in the cosmic dance, witnesses to their planet's stories across eons that dwarf human timescales. They exist in space and time, those fundamental forms of being that philosophers have pondered for millennia, trying to understand what they truly are. Ancient thinkers saw space and time as absolute backdrops against which events occurred, unchanging stages on which the drama of existence played out, containers that held the universe but were not affected by it. But modern understanding, beginning with Einstein's special and general relativity published in 1905 and 1915, reveals that space and time themselves are dynamic, that they curve around massive objects, creating what we experience as gravity, that they're woven together into a four-dimensional fabric called space-time that can stretch and compress, that warps and flows, that is inseparable from matter and energy. Our own moon, Earth's constant companion, has been with us for 4.5 billion years, nearly as long as Earth itself has existed. That duration is almost incomprehensible. Longer than life has existed on land, longer than the continents have held their current shapes, longer than almost anything we can point to on Earth's surface has endured. The Moon has witnessed the entire evolution of complex life on Earth, seen single-celled organisms give rise to multicellular forms, watched as life colonized the land and the air, seen species arise and flourish and go extinct, witnessed ice ages come and go, watched as continents drifted apart and collided and drifted apart again, seen mountain ranges rise and erode away. Everything we know of Earth's history since shortly after its formation, the Moon has witnessed from its silent vantage point in space, circling endlessly, gradually drifting farther away at about 3.8 centimeters per year, as tidal interactions transfer angular momentum from Earth's rotation to the Moon's orbit. For much of human history, for thousands of years across many cultures from Mesopotamia to China to the Americas, from the ancient Egyptians who tracked its phases in their calendars, to the Maya who calculated its motions with remarkable precision, we thought the Moon was the only moon, that we were somehow special, somehow unique in having a companion in the sky. The Moon was mysterious, divine, associated with gods and goddesses across cultures, its phases marking time, its influence on tides, noticed and incorporated into mythology and early science. But no one imagined that other planets might have their own moons, their own satellites circling in the darkness, because the nature of planets themselves was not yet understood. The planets were wandering stars, bright points that moved against the fixed background of constellations, but their true nature as worlds remained unknown. Then, in January of 1610, a pivotal moment in human history occurred. Galileo Galilei, an Italian mathematician and astronomer, turned his telescope toward Jupiter, one of the brightest objects in the night sky. The telescope was a new invention. Galileo had heard of its invention in the Netherlands the previous year and had quickly constructed his own improved version with a magnification of about 20 times. When he pointed it at Jupiter, expecting perhaps to see the planet's disk more clearly, he saw something unexpected. 4 points of light arranged in a line on either side of the planet, like pearls on an invisible string. Night after night, he observed them, carefully recording their positions, watching them move, sometimes disappearing behind Jupiter or in front of it, proving conclusively that they orbited the planet. In that moment, the universe grew larger in human consciousness, expanded beyond what anyone had imagined. We were no longer alone in having a moon, no longer unique in this aspect. The cosmos had suddenly become more crowded, more complex, more wondrous. If Jupiter had moons, what else was out there? By the way, I wonder, where are you watching from tonight? Which city? Which part of the world? Which time zone? And what time of day is it for you right now? Are you experiencing night as I speak of night, darkness outside your window, or does sunlight stream through illuminating your space? Time is local in a profound sense, not just in terms of time zones, but in the physics of relativity. Time literally passes at different rates, depending on gravitational fields and velocities. A clock on GPS satellites runs slightly faster than clocks on Earth's surface because it's farther from Earth's gravitational field where space-time is less curved. These differences are tiny, microseconds per day, but real and measurable, and if we didn't account for them, GPS systems would quickly become inaccurate. Time is not absolute, not the same everywhere, but relative, local, dependent on your motion and location in a gravitational field. Since Galileo's discovery more than 4 centuries ago, since that winter night in 1610, when he recorded his observations and changed humanity's understanding of the cosmos, we've found hundreds more moons throughout our solar system, and the count keeps rising gradually as technology improves and surveys become more sensitive. As of March 2025, more than 891 moons have been confirmed orbiting various bodies throughout our solar system. This number includes moons of many types and sizes, from massive Ganymede larger than the planet Mercury to tiny moonlets just a few kilometers across embedded in Saturn's rings, barely more than rubble piles held together by weak gravity. Of these, nearly 900 moons, 421 orbit the major planets, the 8 planets from Mercury to Neptune, and the officially recognized dwarf planets like Pluto and Eris. Meanwhile, more than 470 additional moons orbit asteroids and trans-Neptunian objects, those distant frozen worlds drifting in the cold outer reaches of the solar system beyond Neptune's orbit, where sunlight is faint, where temperatures hover just above absolute zero, where distances are measured not in millions, but in billions of kilometers. Some asteroids in the main belt between Mars and Jupiter have small companions, binary systems where 2 rocky bodies orbit their common center of mass. Some Kuiper Belt objects beyond Neptune have moons, perhaps formed in collisions or captured gravitationally in the dense early Kuiper Belt, before most objects were scattered by gravitational interactions with Neptune. Each moon, regardless of size, exists in space with definite coordinates that change continuously as it orbits, tracing a path through 3-dimensional space, or more correctly through 4-dimensional space-time. And each exists in time with a history of formation and evolution, stretching back billions of years, and a future that may last billions more years, or end suddenly in a collision with another moon, or with its planet, or in tidal disruption if it drifts too close to its planet and crosses what we call the Roche limit, the distance at which tidal forces overcome the moon's internal structural strength and tear it apart into a ring of debris. Saturn currently holds the record with 274 confirmed moons as of 2025, though this number may continue to rise as surveys discover small irregular moons in distant orbits. Jupiter follows with 97 known satellites. These gas giants, massive and gravitationally powerful, with masses hundreds of times greater than Earth's, act as collectors, gathering moons the way ancient libraries gathered scrolls from across the known world. Each one a fragment of knowledge, each one a fragment of the solar system's history, written in rock and ice that has existed for 4.6 billion years. The atoms that compose these moons, the oxygen and silicon and iron and magnesium, were present in the solar nebula and have simply changed form over time, combining and recombining in different molecules and minerals, but never truly created or destroyed, only transformed, following the law of conservation of mass and energy. Interestingly, not all planets have moons. Mercury and Venus, the 2 planets closest to the Sun, are solitary, orbiting without companions. This absence tells a story just as eloquent as the presence of moons around other planets, speaks of orbital mechanics and gravitational dynamics, and perhaps of violence in the early solar system. Mercury, orbiting at an average distance of just 58 million kilometers from the Sun, where solar heating is intense and solar tides are strong, cannot hold on to a satellite for long. The Sun's gravitational field is too strong, too dominant in that region, and any potential moon would be stripped away or would crash into Mercury within a geologically short time. Scientists believe Mercury may have experienced a catastrophic collision early in its history, during the period of heavy bombardment, when the inner solar system was filled with debris, an impact that stripped away much of its outer silicate mantle and left behind a world that is mostly iron core, covered by a thin shell of rock, giving Mercury an unusually high density for its size. Venus presents a different puzzle, more mysterious in some ways because it's so similar to Earth in size and mass, yet so different in other respects. Venus is nearly Earth's twin, 95% of Earth's diameter at 12,104 kilometers, 82% of Earth's mass, with a similar bulk composition of rock and iron. It sits far enough from the Sun at 108 million kilometers that it should have been able to retain a moon if one had formed through collision or capture, that distance being well beyond the Sun's strongest tidal influence in the realm where Earth has successfully kept its moon for 4.5 billion years. Yet Venus has no moon today, orbits alone, and the reason remains somewhat uncertain, though theories exist. The leading hypothesis, though still debated among planetary scientists because we lack definitive evidence, suggests that Venus did have a moon once long ago in the early solar system, when planets were still settling into their final configurations. Perhaps it formed from a giant impact similar to the collision that created Earth's moon, debris from a catastrophic collision coalescing in orbit over time. But then, this theory continues. Venus experienced a second major impact, another collision from a large body, perhaps an asteroid or planetesimal tens or hundreds of kilometers across, during the final stages of planetary formation, when such impacts were still relatively common. This second impact had two major effects. It knocked Venus into a retrograde spin, making it rotate backward compared to most other planets in the solar system, slowly turning clockwise when viewed from above the North Pole instead of counterclockwise. And it sent Venus's hypothetical moons spiraling inward through complex gravitational interactions and tidal effects. Over millions of years, perhaps tens of millions, that moon would have slowly spiraled inward as tidal interactions between Venus and the moon transferred angular momentum, the moon's orbit decaying gradually, bringing it closer and closer to Venus, until finally it crossed inside what we call the Roche limit, the distance at which tidal forces from the planet exceed the moon's internal structural strength. At that point, the moon would have been torn apart by differential gravity, pulled into elongated shapes, and eventually broken into fragments that either crashed into Venus in a series of impacts or formed a temporary ring system that eventually fell into the planet. The result would be Venus as we see it today, alone, rotating very slowly backward, taking 243 Earth days to complete one rotation, longer than its year of 225 Earth days, making a day on Venus longer than a year, a bizarre inversion unique among the planets. This double impact scenario, while speculative and impossible to prove definitively without somehow examining Venus's interior structure or finding chemical evidence in rocks, would explain both Venus's moonless state and its peculiar rotation. The absence of a moon thus tells a story of violence, of catastrophic collisions in the early solar system, of the chaotic nature of planet formation when worlds were still growing and debris filled the space between orbits. Every absence contains information, Every empty space where something might be, but isn't, speaks to us about history and process, and the contingent nature of how the solar system came to have its current configuration. To understand moons in their full complexity, to really appreciate what they are and how they came to be, and why they're so diverse, we must journey back through time. Not metaphorically, but in a real sense, tracing the history of matter backward through billions of years to its origins. Close your eyes again if they've opened, and imagine that we're moving backward through time, watching the clock run in reverse, watching the solar system grow younger, the sun shrinking and cooling, the planets moving backward in their orbits. 4.6 billion years ago, back before any of the planets or moons existed in their current forms, there was a vast cloud of gas and dust floating in interstellar space, a molecular cloud hundreds of billions of kilometers across, cold and dark, composed primarily of hydrogen and helium, left over from the Big Bang 13.8 billion years earlier, plus heavier elements forged in previous generations of stars and scattered into space when those stars died in supernova explosions or shed their outer layers as planetary nebulae. This cloud was part of a much larger complex of clouds, drifting through our galaxy, slowly rotating with the galaxy's rotation, moving through space at hundreds of kilometers per second, though appearing nearly motionless to any hypothetical observer because of the vast scales involved. For millions of years it drifted, gradually cooling, slowly contracting under its own gravity, dense enough that gravity pulled inward, but turbulent enough, and pressure supported enough that it remained in rough equilibrium, neither collapsing nor dispersing. Then something happened. Perhaps a nearby supernova explosion sent a shockwave through the region, compressing the cloud. Perhaps two clouds collided, creating a region of increased density. Perhaps it was simply a random fluctuation, a region that happened by chance to be slightly denser than average. And once it began contracting, the contraction became self-reinforcing as increased density meant stronger gravity, which caused faster contraction, which increased density further. Whatever the trigger, the cloud began to collapse. As it collapsed over hundreds of thousands of years, as material fell inward under gravity's pull, the cloud began to spin faster and faster. This is a fundamental consequence of the conservation of angular momentum, a principle as fundamental as the conservation of energy, which states that the total angular momentum of a closed system remains constant unless external torques act on it. The cloud had some initial rotation, inherited from the galaxy's rotation and from turbulent motions within the cloud, and as it shrank, that rotation had to speed up, just as a figure skater spins faster when they pull their arms in. The collapsing cloud spun faster and faster, and centrifugal effects began to matter. Material could fall freely toward the center along the rotation axis where centrifugal force was negligible, but material at the equator was flung outward by rotation. The result was that the cloud flattened from a roughly spherical shape into a rotating disk, the protoplanetary disk, with most of the mass concentrated at the center, where pressure and temperature were climbing as gravitational potential energy converted to heat. At the center, as more and more material accumulated, the proto-sun formed, growing denser and hotter, pressure at its core rising, until after perhaps a few 100,000 years, it reached 10 million degrees Kelvin, hot enough for nuclear fusion to begin. Hydrogen nuclei, protons, began fusing into helium, releasing enormous energy according to Einstein's famous equation, EOMC2. And our sun was born, beginning to shine with light that would eventually reach across billions of kilometers of space to illuminate planets and moons that had not yet formed. In the disk surrounding this newborn star, in that flat, rotating structure of gas and dust orbiting the sun, like a cosmic record spinning on a turntable, the next phase of formation began. The disk was not uniform, but varied in density and composition with distance from the sun. Close to the sun, where temperatures were high, only materials with high melting points could condense from the vapor phase. Metals like iron and nickel, minerals like silicates that make up rock. Volatile materials like water and methane and ammonia remained gaseous and were blown outward by the solar wind and by radiation pressure from the luminous proto-sun. Farther out, where temperatures were lower, beyond what we call the frost line or snow line located somewhere around where the asteroid belt is today, water ice could condense and exist as solid particles. In this disk, particles began to stick together. At first, it was microscopic dust grains colliding and adhering through electrostatic forces and van der Waals forces, weak intermolecular attractions that could hold small particles together. These grains slowly grew into millimeter-sized pebbles, then centimeter-sized aggregates, then meter-sized boulders, each collision potentially adding mass or potentially shattering the aggregate, depending on the velocity and angle of impact. This process is called accretion, and it operated on timescales of millions of years, requiring patience beyond human comprehension. As these bodies grew larger, their gravity began to matter, began to pull in nearby material more efficiently. Bodies that happened to be slightly larger than average had an advantage. They could accrete material faster, growing even larger, clearing zones around their orbits. Eventually, over perhaps 10 million years, a blink in cosmic time but an eternity by human standards, kilometer-sized planetesimals formed, then 10-kilometer bodies, then 100-kilometer embryos. These protoplanets orbited the Sun, occasionally colliding with each other in violent impacts that either merged them into larger bodies or shattered one or both into fragments. The process was chaotic, statistical, governed by probability and orbital dynamics. Some regions of the disk cleared faster than others. In the inner solar system, where orbital velocities were high and material was relatively sparse, the terrestrial planets formed: Mercury, Venus, Earth, Mars, rocky worlds composed primarily of silicates and iron, because only those materials could condense at high temperatures. In the outer solar system beyond the frost line, where temperatures were lower and ice was abundant, much more mass was available for planet formation, because ice is far more abundant than rock when you include all the hydrogen and oxygen that forms water. The protoplanets that formed there could grow much larger, and once they reached perhaps 10 Earth masses, their gravity became strong enough to capture hydrogen and helium gas directly from the surrounding nebula. These became the gas giants, Jupiter and Saturn, massive worlds with small rocky cores surrounded by enormous envelopes of hydrogen and helium, growing to hundreds of Earth masses. Farther out still, where the density of material was lower and formation timescales longer, Uranus and Neptune formed as ice giants, smaller than Jupiter and Saturn, composed largely of water, methane and ammonia ices, with smaller atmospheres of hydrogen and helium. But the story didn't end there with planet formation, didn't stop once the major planets had formed and cleared their orbital zones of most debris. Around the largest planets, particularly the gas giants forming in the outer solar system, where material was more abundant, smaller disks of material formed within the larger protoplanetary disk, circumplanetary disks, miniature versions of the great disk that birthed the solar system itself. These were created from material that was captured by the growing planet's gravity as it swept through the protoplanetary disk like a vacuum cleaner, but material that didn't fall directly into the planet because it had too much angular momentum, too much sideways motion relative to the planet. This material retained enough orbital energy to circle the planet, rather than falling straight in, creating a disk that orbited the planet the way the larger protoplanetary disk orbited the Sun. From these circumplanetary disks, moons were born through processes similar to planet formation, but on a smaller scale and operating more quickly because the disks were smaller and denser. Material in the circumplanetary disk began to accrete, sticking together bit by bit, particle by particle, following the same basic process that formed planets but compressed in space and time. Layer upon layer, built up like pearls, forming around grains of sand in an oyster, slowly coalescing over hundreds of thousands of years through collisions and gravitational attraction, perhaps a few million years for the largest moons like Ganymede and Titan, which grew to thousands of kilometers in diameter. As they grew, these moons swept up material from their orbital zones in the circumplanetary disk, clearing lanes around themselves, creating gaps similar to the gaps that planets created in the protoplanetary disk. This is how the regular moons formed. The moons we sometimes call regular satellites to distinguish them from irregular captured moons. Moons like the Galilean satellites of Jupiter and the major moons of Saturn like Titan and Rhea and the others. These regular moons orbit in neat, nearly circular paths, aligned with their planet's equator within a few degrees, following the plane of the original circumplanetary disk from which they emerged. Their orbits preserve the memory of that disk's orientation. Billions of years after the disk itself dissipated, after the gas was blown away by the solar wind, and the remaining solid material was either accreted into moons or ejected from the system through gravitational interactions. These regular moons are children of their planets in a real and profound sense, born from the same material that surrounded the planet during its formation, shaped by the same processes, their composition reflecting the temperature and pressure and chemical conditions in that part of the solar system at that time in history when they were forming 4.5 billion years ago. Their orbits are prograde, meaning they move in the same direction as their planet's rotation, counterclockwise when viewed from above the solar system's north pole, following the convention established by the International Astronomical Union for defining directions in the solar system. They follow the ancient momentum of the circumplanetary disk from which they emerged, a memory of rotation encoded not in conscious minds, but in orbital motion, in the angular momentum that has been preserved across billions of years of orbital evolution. These regular moons, formed over millions of years through patient accretion, slowly coalescing in the rotating disk, growing larger as they swept up material in their orbital paths, through gravitational attraction and through occasional gentle collisions that added mass rather than shattering the growing moon. The process required time, required countless collisions, required the gradual accumulation of matter atom by atom, molecule by molecule, grain by grain, following processes that we're only now beginning to understand fully through computer simulations that can model the complex gravitational interactions and collisional dynamics involved in moon formation. But not all moons form this way through orderly accretion in circumplanetary disks, through patient accumulation over millions of years in a rotating disk of gas and dust. The solar system is more complex, more diverse than any single formation mechanism could produce. Some moons are captured worlds, asteroids or comets or Kuiper belt objects that formed elsewhere in the solar system, that traced their own independent orbits around the Sun for millions or billions of years, wandering through space following their own trajectories, until they wandered too close to a planet's gravity well and were pulled into orbit through a process called gravitational capture. Capture is actually quite difficult in celestial mechanics, rarer than you might expect, because normally an object approaching a planet on a hyperbolic trajectory, moving faster than the planet's escape velocity, will simply swing past in a hyperbolic arc and escape back into independent orbit, continuing on its way like a comet passing near the Sun. For capture to occur, the approaching object needs to lose energy somehow, needs to be slowed down below the escape velocity so that it becomes bound to the planet. This usually requires a three-body interaction where a third body, perhaps another moon already orbiting the planet, or perhaps a close encounter with the planet's atmosphere, if it has a substantial one, absorbs some of the incoming object's kinetic energy through a gravitational interaction or through atmospheric drag, slowing it down just enough that it can no longer escape. Alternatively, capture can occur during a time when the planet is still forming and surrounded by a dense circumplanetary disk of gas. The incoming object can be slowed by drag with the gas, losing velocity as it plows through the disk like a meteor entering Earth's atmosphere, and this can remove enough energy to trap it in orbit. This mechanism would only work early in the solar system's history, when circumplanetary disks still existed, in the first few million years after planet formation. Objects captured this way would then slowly spiral inward through the gas disk until the disk dissipated. These irregular moons, as we call them in planetary science to distinguish them from regular moons, formed in circumplanetary disks, often have tilted elliptical orbits that betray their foreign origins, orbits that are inclined at steep angles to their planet's equator, sometimes 30 or 40 or even 60 degrees or more, that mark them as outsiders, as immigrants to their current systems who came from elsewhere, who remember in their orbits the independent existence they once had. They don't follow the rules that the regular moons follow, don't orbit in the neat circular paths aligned with their planet's equator. They move retrograde sometimes, backward relative to their planet's rotation, orbiting clockwise when viewed from above the North Pole when everything else orbits counterclockwise, as if remembering the freedom they once had, the independent heliocentric orbits they traced before capture, orbits around the Sun rather than around a planet, paths that took them throughout the solar system on their own trajectories, determined by their initial conditions and by gravitational perturbations from the planets. Their orbits are often highly eccentric as well, not circular but elongated ellipses that take them far from their planet at apoapsis and close at periapsis, orbits that reflect the chaotic nature of their capture rather than the orderly formation in a circumplanetary disk. And they may be found far from their host planet, orbiting at great distances, measured in millions of kilometers, where the planet's gravity is weaker but still sufficient to hold them against perturbations from the Sun and from other planets, captured perhaps during a moment of gravitational opportunism, billions of years ago, when conditions were just right, when velocities and angles aligned in precisely the way needed for capture to occur. Neptune's Triton stands as the most famous and dramatic example of a captured moon in our solar system, a moon whose very existence tells a story of violence and chaos in the early outer solar system. Triton is large, 2,700 kilometers across, almost as large as our own moon, and substantially larger than Pluto. Yet it orbits Neptune backward, retrograde, moving clockwise when viewed from above the North Pole, while Neptune rotates counterclockwise. Its orbit is nearly circular now, but tilted 157 degrees to Neptune's equator, almost perpendicular to the planet's orbital plane. Everything about Triton's orbit screams captured object, and scientists are confident that it originated in the Kuiper Belt, that distant realm of icy bodies beyond Neptune, where Pluto resides along with Eris and Makemake and Haumea, and thousands of other objects ranging from a few kilometers to thousands of kilometers across. Triton's capture billions of years ago, perhaps 3 to 4 billion years ago, based on models of orbital evolution, would have been a violent, catastrophic event in Neptune's history, one of the most dramatic gravitational events in the outer solar system. When Triton encountered Neptune, probably coming in from a distant orbit, probably moving at high velocity, some mechanism, perhaps a three-body interaction with another Kuiper Belt object, perhaps drag from a circumplanetary disk, if any still existed at that late date, removed enough energy to trap it in orbit. But its initial orbit would have been highly elliptical, taking it far from Neptune and then close in repeated passes. Over millions of years, tidal interactions between Neptune and Triton circularized the orbit, but at a terrible cost to Neptune's original moon system. Neptune likely had a system of regular moons formed from its circumplanetary disk, moons comparable perhaps to the moons of Uranus, orbiting in neat circular paths aligned with Neptune's equator. Triton's capture disrupted this system catastrophically. Gravitational interactions with the massive intruder sent these original moons into chaotic orbits, some crashing into each other in high-velocity collisions that shattered them into fragments, others spiraling into Neptune to be consumed and merged with the planet's mass, still others perhaps being ejected from the system entirely, flung into independent orbits around the Sun. The process would have taken millions of years as Triton's orbit slowly circularized and the system settled into its current configuration. But the end result is clear. Today, Neptune has Triton as its dominant satellite, massive and alone in a circular retrograde orbit, with only a handful of small irregular moons remaining as possible survivors of the original system or later captures from the Kuiper Belt population. And then there's the third major formation mechanism. Moons born from violence like our own moon, worlds created in giant impacts that are among the most energetic events in the history of the solar system, short of supernova explosions. The giant impact hypothesis, explaining our moon's origin, has become the leading theory over the past few decades, supported by decades of computer simulations modeling impacts with ever-increasing resolution and sophistication, and by chemical analysis of lunar rocks and soil brought back by Apollo astronauts between 1969 and 1972 during humanity's brief visits to another world. The hypothesis suggests that early in Earth's history, about 4.5 billion years ago, when the solar system was still young and chaotic, when impacts were common because the inner solar system was still being cleared of debris through gravitational interactions and collisions, a Mars-sized body that we've named Theia, after the Greek Titaness who was the mother of Selene. The moon goddess collided with our young planet. This wasn't a head-on collision, but an off-center glancing impact, the two bodies sideswiping each other at tremendous velocity, perhaps 4 kilometers per second or faster, with an angle calculated to be about 45 degrees from direct impact. The impact was catastrophic beyond anything we can easily imagine, one of the most violent events Earth has ever experienced. It released energy equivalent to hundreds of millions of megatons of TNT, billions of nuclear weapons all detonating at once, enough to vaporize much of Theia's mass instantly and liquefy Earth's entire surface for thousands of kilometers around the impact site. The collision tore away a huge chunk of Earth's mantle, the layer of hot rock between the core and the crust composed of silicate minerals like olivine and pyroxene, and vaporized much of both Theia's and Earth's mantles, creating a massive crater that would have glowed white-hot, temperatures reaching thousands of degrees. The energy of the impact sent debris spiraling into orbit around the wounded Earth, a ring of molten rock and vaporized silicates surrounding our planet like the rings around Saturn, but made of molten and vaporized rock instead of ice particles, glowing red and orange with heat, extending tens of thousands of kilometers into space. Some material fell back to Earth immediately, raining down as molten droplets, but material with sufficient angular momentum remained in orbit, circling the Earth in an incandescent ring that gradually cooled and settled into the planet's equatorial plane. From that debris ring, over time measured in years to centuries, as the material cooled from thousands of degrees down to temperatures where it could solidify, our moon formed through accretion. Particles in the ring collided and stuck together, gradually clumping into larger bodies. The process would have been relatively quick on geological timescales. Computer simulations suggest the moon could have formed in anywhere from a few years to a few centuries, remarkably fast compared to the millions of years required to form planets or moons in circumplanetary disks. The newly formed moon was much closer to Earth than it is today, perhaps just 20,000 to 30,000 kilometers away compared to today's 384,000 kilometers. And it was molten, a sphere of liquid rocks slowly cooling over millions of years, solidifying from the outside in as heat radiated away into the vacuum of space. Our moon is thus a child of collision, born from violence and catastrophe, a reminder that beauty can emerge from chaos and destruction, that some of the most stable and enduring structures in the universe arose from moments of extreme violence. The impact probably also tilted Earth's rotation axis, giving us our 23.5-degree axial tilt that creates our seasons, the annual cycle of summer and winter that has shaped life's evolution on Earth. This giant impact hypothesis explains many observations that puzzled scientists for decades. Why the moon's composition is so similar to Earth's mantle in terms of oxygen isotopes, which serve as a chemical fingerprint revealing where material formed in the solar system. Why the moon is depleted in volatile elements that would have been vaporized in the impact. why it lacks a substantial iron core proportional to its size. Because it formed from the mantles of Earth and Theia, not from their cores which remained in Earth after the impact and sank to the center under gravity, and why the Earth-Moon system has such high total angular momentum, such high combined rotation and orbital motion. Charon, the largest moon of Pluto orbiting the dwarf planet at just 19,600 kilometers center-to-center distance, is thought to have formed in a similar way through a giant impact, another collision creating another double world in the outer solar system, though on a smaller scale with lower velocities and less total energy involved, because Pluto is so much smaller and less massive than Earth, just 1/6 of 1% of Earth's mass. The impact that created Charon may have also created Pluto's 4 smaller moons, Styx, Nix, Kerberos, and Hydra, from the debris that didn't coalesce into Charon, fragments that remained in orbit around the Pluto-Charon system. Small, irregular bodies just tens of kilometers across, tumbling chaotically as they orbit. Pluto and Charon are so close in size, with Charon being about half Pluto's diameter at 1,212 kilometers compared to Pluto's 2,377 kilometers, that they truly form a binary system rather than a simple planet-moon system in the traditional sense. The center of mass of the system, the barycenter around which both bodies orbit, lies in the space between them rather than inside either body, about 2,000 kilometers outside Pluto's surface. Both Pluto and Charon orbit this point in space, completing one mutual orbit every 6,387 days. And they're mutually tidally locked, a unique configuration in the solar system. Not only does Charon always show the same face to Pluto as our moon does to Earth, but Pluto always shows the same face to Charon. They're frozen in an eternal gaze across the 19,600 kilometers that separate them, synchronized perfectly in their rotation and orbit like partners in a dance who never break eye contact, who move together as one. So you see, when you examine all the evidence we've gathered from spacecraft missions and telescopic observations, when you contemplate the full diversity of moons and their characteristics and origins, moons are diverse not just in their present forms, in their sizes ranging from a few kilometers across up to larger than the planet Mercury, in their compositions ranging from pure water ice to solid rock to complex mixtures, in their surface features from heavily cratered ancient terrain to smooth young plains to actively erupting volcanoes, but also fundamentally in their origins, their birth stories, the processes that created them billions of years ago when the solar system was young. Some were built patiently in circumplanetary disks through accretion, growing slowly over millions of years like miniature planets. Some were captured from wandering trajectories, finding new homes around massive planets through chance encounters. Some were torn from catastrophe, born in violence and fire, created in moments of destruction that lasted just hours or days, but gave rise to new worlds that have existed for billions of years since then. Let us journey now to Jupiter, the king of planets, the largest world in our solar system, and meet its 4 largest moons discovered by Galileo 4 centuries ago. Jupiter is massive, 318 times Earth's mass, more massive than all other planets combined, large enough that if it were about 80 times more massive, it would have ignited nuclear fusion and become a star rather than a planet. It orbits the Sun at 778 million kilometers, or 5.2 astronomical units, taking nearly 12 Earth years to complete one orbit. Despite its size, it rotates rapidly, completing one rotation in just under 10 hours, making it the fastest rotating planet in the solar system. And this rapid rotation flattens it noticeably at the poles. Its equatorial diameter is about 7% larger than its polar diameter. Jupiter has 97 known moons as of 2025, but 4 dominate: the Galilean satellites Io, Europa, Ganymede, and Callisto, named eventually, though not by Galileo himself, after lovers and favorites of the god Jupiter in Roman mythology. These are not mere rocks spinning in space, not just gravitationally bound debris. They are worlds, complete worlds, each with its own character, its own unique geology, its own story written in the language of chemistry and physics and time, in the evidence preserved in their surfaces and inferred about their interiors from gravitational measurements made by spacecraft flying past, from magnetic field observations, from spectroscopic analysis of their surfaces. They formed from Jupiter's circumplanetary disk billions of years ago, when Jupiter was young and still accreting gas from the solar nebula, growing to become the most massive planet. And together, they represent a miniature solar system, a family of worlds bound to the largest planet, showing us how diverse moons can be, even when they form in the same system from similar starting materials within the same circumplanetary disk orbiting the same planet. Different distances from Jupiter, different amounts of tidal heating, different compositions. These factors combined to create 4 completely distinct worlds. Io is a world of fire, a world of constant transformation, unlike anything else we've seen in our exploration of the solar system, the most volcanically active body we know of by far. Its surface is constantly resurfacing itself with fresh lava at a rate faster than any other known world, erupting about 100 times more lava per unit area than Earth, covering over its impact craters within a few million years, erasing evidence of ancient bombardment. More than 400 active volcanoes dot its relatively small surface. Io is just 3,643 kilometers in diameter, slightly larger than our moon, but smaller than the other Galilean satellites, some erupting continuously for decades or longer, as observed by multiple spacecraft missions from Voyager to Galileo to Juno. Others episodically in outbursts that can change the landscape dramatically within weeks or months. Why is Io so active? Why does it have so much internal heat when moons of similar or larger size like our moon and Callisto are geologically dead, their interiors frozen solid billions of years ago, their surfaces preserving ancient craters? The answer lies in gravitational interactions, in the complex dance of moons around Jupiter. Io is caught in a gravitational tug-of-war between Jupiter and the other Galilean moons, particularly Europa and Ganymede, which are locked in orbital resonances with Io in a configuration called a Laplace resonance, discovered by the mathematician Pierre-Simon Laplace in the 18th century. For every one orbit Io completes around Jupiter in 1.77 days, Europa completes exactly 2 orbits in 3.55 days, and Ganymede completes exactly 4 orbits in 7.15 days. These are mathematical ratios, 1.2.4, that create repeating configurations where the moons align in the same relative positions periodically, their gravitational effects reinforcing each other. This resonance prevents Io's orbit from becoming perfectly circular. Europa and Ganymede's gravitational tugs maintain a slight eccentricity in Io's orbit, just 0.0421, a tiny deviation from perfect circularity, but enough to matter enormously. As Io moves slightly closer to and farther from Jupiter during each orbit, due to this eccentricity, Jupiter's enormous gravitational field flexes Io's interior in changing ways. When Io is closer to Jupiter at periapsis, it feels stronger tidal forces and is squeezed more. When it's farther at apoapsis, the tidal forces are weaker and Io relaxes slightly. This constant flexing, Io's shape changing by up to 100 meters in height during each 1.77-day orbit, generates enormous internal friction as rock and magma are forced to deform continuously. It's the same principle as bending a wire back and forth. The wire heats up from the mechanical work being converted to heat through friction at the molecular level. This tidal heating keeps Io's interior molten, keeps it churning with magma, probably throughout much of the mantle, generates perhaps 100 trillion watts of heat continuously, keeps it alive with fire, despite being far from the sun, where solar heating provides less than 4% of the heat that Earth receives. The tidal forces are so strong, so relentless, operating every 1.77 days as Io completes each orbit, that Io's surface literally rises and falls like an extreme tide, with the land itself moving up and down, solid rock and sulfur compounds behaving almost like a viscous fluid under Jupiter's immense gravitational pull. If you could stand on Io's surface, though you wouldn't survive long in its thin, toxic atmosphere of sulfur dioxide gas at only 1/1000th the pressure of Earth's atmosphere, and you'd be bombarded by intense radiation from Jupiter's magnetosphere that would deliver a lethal dose within hours, you would see a landscape alien beyond imagining. Plumes of volcanic material erupting constantly from active vents, some reaching heights of 300 to 500 kilometers into the sky, higher than the International Space Station orbits Earth, far above Io's thin atmosphere into the vacuum of space, where the plumes create enormous umbrella-shaped clouds visible from orbit. The surface painted in yellows, oranges, reds and whites from various sulfur compounds, elemental sulfur in different allotropic forms that have different colors depending on temperature and molecular structure. Sulfur dioxide frost that appears white, perhaps some silicate materials as well, though most of Io's lavas appear to be sulfur-rich, based on spectroscopic analysis. Volcanic mountains rise taller than Everest from plains of frozen sulfur dioxide, some reaching 17 kilometers high. Vast lava plains stretch to the horizon, some glowing red or orange in active flow regions, where molten material moves across the surface at temperatures reaching 1,600 degrees Celsius. Calderas, volcanic craters formed when magma chambers empty and the surface collapses. Wider than entire countries on Earth, some more than 200 kilometers across. Larger than Yellowstone caldera, containing lava lakes that rise and fall as magma moves beneath. The surface temperature varies wildly over short distances, from minus 163 degrees Celsius in permanently shadowed regions where sulfur dioxide freezes solid, to over 1,600 degrees Celsius in active lava flows, creating temperature gradients more extreme than anywhere else in the solar system, except perhaps close to the Sun itself. Io loses about 1 ton of material per second to space, about 30 million tons per year, blown away by Jupiter's powerful magnetosphere, which sweeps past Io at tremendous velocity of 74 kilometers per second relative to Io's surface, stripping away the volcanic plumes and ionizing the particles, creating a torus of glowing plasma around Jupiter at Io's orbital distance that emits radio waves detectable from Earth. Yet, despite this constant loss of mass, Io remains geologically young. its surface showing almost no impact craters because they're covered over so quickly by volcanic activity that resurfacing occurs faster than impacts can create new craters. Time on Io is measured not in billions of years, but in much shorter spans. Individual lava flows cool and solidify in weeks or months. Volcanic edifices build up over thousands to millions of years. The entire surface refreshes itself over just a few million years, making Io one of the youngest surfaces in the solar system. Next comes Europa, wrapped in ice that gleams bright white reflecting sunlight. One of the most intriguing and potentially habitable worlds in the solar system. A place that has captured the imagination of planetary scientists and astrobiologists since the Voyager missions first revealed its cracked surface in 1979. Beneath its cracked, crisscrossed shell of water ice lies something extraordinary, something that may be among the most profound discoveries in the history of planetary science. If future missions confirm what models suggest, a global ocean of liquid water, perhaps twice the volume of all Earth's oceans combined, may be 100 kilometers deep, according to models based on gravitational measurements and magnetic field observations from the Galileo spacecraft. The ice shell above is relatively thin in geological terms compared to Europa's 1,560-kilometer radius, though recent estimates have revised our understanding. Data from NASA's Juno spacecraft using microwave radiometry, analyzing radiation emitted naturally by Europa at different wavelengths that penetrate to different depths, suggest the ice shell may be between 20 and 35 kilometers thick, perhaps averaging around 35 kilometers, according to observations published in 2024. This is thicker than earlier models suggested that estimated perhaps 10 to 15 kilometers based on tidal flexing observations, but still thin enough that the ocean beneath might interact with the surface through cracks and upwelling zones where warmer ice rises from depth, carrying dissolved materials from the ocean, or where the shell is particularly thin and might occasionally break through, creating temporary connections between ocean and space. Beneath that ice shell, in eternal darkness that has persisted for billions of years, that has never been illuminated by direct sunlight, that ocean sloshes and flows according to complex dynamics we're only beginning to understand. It's warmed not by the sun, but by tidal heating, generated by Europa's slightly eccentric orbit. As Europa moves closer to and farther from Jupiter during each 3.55-day orbit, tidal forces flex its interior, generating heat through friction, perhaps 100 million watts continuously according to models, enough to keep water liquid despite surface temperatures of minus 160 degrees Celsius. The ocean has likely existed for billions of years, as long as Europa has existed, providing stable conditions over geological time where life could potentially arise if the chemistry is right. The ocean may be in direct contact with a rocky seafloor at the base of the ocean, beneath perhaps 100 kilometers of water, where hydrothermal vents could exist similar to those on Earth's ocean floors. Hot water, rich in dissolved minerals and gases, could erupt from cracks in the crust, where seawater seeps down into hot rocks and is heated by residual heat from Europa's formation and from radioactive decay of uranium, thorium, and potassium in the rocks. These vents would create chemical gradients and provide chemical energy that on Earth supports entire ecosystems independent of sunlight. Life powered not by photosynthesis, converting light to chemical energy, but by chemosynthesis, where bacteria and archaea oxidize chemicals like hydrogen, sulfide, and methane to extract energy, creating organic compounds that support food chains extending upward to larger organisms like tube worms and crabs and fish that cluster around the vents in Earth's deep oceans. Could similar life exist in Europa's ocean, swimming in those dark waters that have never seen sunlight, adapted to eternal night, thriving on chemical energy alone? We don't know, cannot know without sending a probe to drill through the ice or sample material from plumes if they exist, or somehow access the ocean. But the possibility is tantalizing enough that NASA has devoted billions of dollars and decades of planning to the Europa Clipper mission launched in October 2024, currently on its way to Jupiter, where it will arrive in the early 2030s after a journey of about 6 years, using gravity assists from Mars and Earth to gain velocity. The surface of Europa tells a story of dynamic processes operating over millions of years. It shows long linear fractures called lineae, crisscrossing the ice like cracks in the shell of a boiled egg, some extending for thousands of kilometers, formed perhaps as the ice shell flexes and cracks under tidal stresses, or as the shell expands and contracts with temperature changes. There are ridges rising hundreds of meters above the surrounding plains, double ridges with parallel crests separated by central troughs, formed perhaps when water or warmer ice wells up through cracks and freezes, building up the ridge over many eruption cycles. And there's chaotic terrain where the ice has broken into jumbled blocks that have rotated and tilted before refreezing, suggesting that the ice shell has broken through to liquid water or warmer ice below that allowed the blocks to move before refreezing, locked them in their current positions. The reddish-brown streaks visible in high-resolution images from spacecraft, particularly visible in false color images that enhance subtle color variations, may be the most intriguing surface features. Spectroscopy, analyzing reflected sunlight to determine chemical composition, suggests these colored regions contain salts like sodium chloride, common table salt, or sulfate minerals mixed with organic compounds, material from the ocean below that has worked its way to the surface through cracks and upwelling zones, reaching the surface and being altered by radiation from Jupiter's intense magnetosphere, which slowly breaks apart molecules and causes chemical reactions. The presence of salts is particularly interesting because it indicates the ocean is salty like Earth's oceans, which is important for habitability. Pure water has different properties than salt water, and the right salinity is important for many biological processes. Europa has become one of our most compelling targets in the search for life beyond Earth, a place where all the ingredients necessary for life as we know it, liquid water existing stably for billions of years, chemical energy from hydrothermal activity, organic compounds delivered by impacts or created through chemical reactions, and relatively stable conditions protected from radiation by kilometers of ice, may exist together. The ice shell shields the ocean from Jupiter's intense radiation that would quickly destroy complex organic molecules on the surface, creating a protected environment where chemistry can operate for billions of years. Time on Europa operates on multiple scales. The surface refreshes itself over tens of millions of years, as impacts create new craters and tectonic processes create new lineae. The ice shell responds to tidal forces during each 3.55-day orbit, flexing slightly, and the ocean has existed for billions of years since Europa formed, providing the long timescales that life might require to arise and evolve. Ganymede is the giant among giants, the colossus among moons, the largest moon in the entire solar system, larger even than the planet Mercury at 5,268 kilometers diameter compared to Mercury's 4,280 kilometers. If Ganymede orbited the Sun independently instead of Jupiter, if it had formed as an independent body rather than in Jupiter's circumplanetary disk, it would easily qualify as a planet in its own right, perhaps even a major planet, rather than a dwarf planet given its size and mass of 148 billion trillion kilograms. It is the ninth largest object orbiting the Sun after the 8 planets, more massive than Pluto and Eris combined. Ganymede is unique among all moons in having its own internally generated magnetic field rather than an induced field created by interaction with Jupiter's magnetosphere. The magnetic field is produced by a dynamo process deep within Ganymede, convection of liquid iron in a molten outer core surrounding a solid inner core, similar to the process that generates Earth's magnetic field. This suggests that Ganymede has differentiated into layers like terrestrial planets, a solid inner core of iron and iron sulfides, perhaps 500 kilometers in radius, a liquid outer core perhaps 400 kilometers thick where the dynamo operates, a rocky mantle of silicates extending another 1,200 kilometers, and finally, a thick outer shell of ice and water perhaps 800 kilometers deep. This internal structure is more complex than most moons, almost planet-like in its organization, showing that large moons can evolve internal structures as complex as planets if they're massive enough and formed with sufficient radioactive elements to provide heat. Ganymede's surface tells a story of geological evolution spanning billions of years, showing 2 distinct terrains that speak of different eras in the Moon's history. About 40% of the surface consists of old, dark terrain, heavily cratered and ancient, some of the oldest surfaces in the solar system, dating back perhaps 4 billion years to shortly after Ganymede formed. This ancient terrain is dark because of impurities embedded in the ice over billions of years, meteoritic material deposited by countless small impacts, organic compounds created by radiation processing, where high-energy particles from Jupiter's magnetosphere break apart molecules and allow them to recombine into more complex forms, all gradually darkening the originally bright ice like soot darkening snow. The remaining 60% consists of younger, lighter grooved terrain that shows signs of tectonic activity unprecedented on other icy moons. Parallel ridges and valleys stretch for hundreds of kilometers, suggesting that the icy crust has been stretched and fractured over time, pulled apart by internal processes that created extensional features. These grooves may have formed when Ganymede's interior expanded, perhaps when it differentiated and the formation of the dense iron core caused the outer layers to expand and crack the surface. Or perhaps during periods when Ganymede's orbit was more eccentric and tidal heating was stronger, warming the interior and causing expansion. The process created the striking pattern of alternating light and dark terrain that makes Ganymede look almost striped in some images, ancient cratered terrain next to younger grooved regions, a patchwork recording billions of years of geological history. Like Europa, Ganymede may also harbor a subsurface ocean, another hidden sea locked beneath kilometers of ice, according to magnetic field observations from the Galileo spacecraft that detected variations consistent with a conducting layer, salt water, at depth. But Ganymede's internal structure may be even more complex and surprising. Models suggest there may be multiple layers of ice and water stacked within Ganymede at different depths, like the layers of an onion, separated by different forms of ice that exist only under extreme pressure. At the base of the ice shell, perhaps 150 kilometers below the surface, there may be a layer of liquid water. Below that, under the pressure of overlying ice, water transitions to high-pressure ice forms, ice VI and ice 7th, crystalline structures where water molecules are packed more densely than in ordinary ice, denser even than liquid water, so they sink rather than float. These high-pressure ices form a layer perhaps 400 kilometers thick. Below that may be another ocean of liquid water kept from freezing by the pressure and by heat from the rocky interior. And below that, the rocky mantle and metallic core. This layered sandwich structure, ice, water, rock, metal, is unlike anything else we've seen in the solar system, a complexity we hadn't anticipated before detailed modeling of Ganymede's interior. Time on Ganymede is measured in billions of years. Its ancient terrain preserves craters from 4 billion years ago. Its grooved terrain is perhaps 1 to 2 billion years old. Everything moving slowly on geological timescales. Ganymede is massive enough and complex enough that some scientists argue it should be considered a planet in its own right, rather than merely a moon. But by current definitions, it orbits Jupiter rather than the Sun directly, and so it remains classified as a satellite, though it rivals many planets in size and exceeds some in geological complexity. And finally, Callisto, the outermost Galilean moon orbiting at 1.88 million kilometers from Jupiter, the most ancient, most cratered, most heavily scarred. Its surface is one long continuous record of bombardment stretching back billions of years. A scarred face that has seen the late heavy bombardment of the early solar system and recorded every blow in craters large and small, from tiny pits just meters across to massive multi-ring impact basins hundreds of kilometers wide. Callisto has changed little since its formation 4.5 billion years ago, perhaps less changed than any other large moon in the solar system. Unlike its siblings with their dynamic surfaces renewed by volcanism or tectonics, Callisto shows no signs of significant geological activity. No grooved terrain like Ganymede, no volcanic resurfacing like Io, no signs of a young surface like Europa. It is a time capsule frozen not just in ice but in history, its surface preserving the conditions and crater distribution of the early solar system. Like a photograph preserves a moment, like tree rings preserve climate history, like sediment layers preserve ancient environments. Its surface is dark, the darkest of the Galilean moons, with an albedo of only about 20%. Much darker than Europa's bright 65%, coated in a mixture of ice and rock, dirty ice that has been darkened by billions of years of meteoritic bombardment, depositing dark carbonaceous material, and by radiation from Jupiter's magnetosphere. Though Callisto orbits far enough out that radiation is much less intense than at Io or Europa. Valhalla Basin dominates one hemisphere, a massive multi-ring impact structure 3,800 kilometers across, larger than the Mediterranean Sea, one of the largest impact structures in the solar system. It was created billions of years ago, when an asteroid, perhaps tens of kilometers across, struck Callisto with tremendous energy, excavating a crater and fracturing the icy crust in concentric rings, radiating outward like ripples in a pond, frozen ripples preserved for billions of years. Because Callisto's surface is so geologically dead, that even such enormous features remain essentially unchanged. The impact would have been catastrophic, releasing energy equivalent to billions of nuclear weapons, briefly melting or vaporizing ice for hundreds of kilometers around the impact point, sending ejecta flying thousands of kilometers before it fell back to the surface. Yet even Callisto, ancient and seemingly inert, seemingly unchanged for billions of years, may hide secrets beneath its battered surface. Evidence from the Galileo spacecraft's magnetic field measurements suggests Callisto too may have a subsurface ocean at depth, a quiet sea that has never seen the light of the sun, locked away in darkness beneath perhaps 200 kilometers of ice and rock, according to models. The ocean would be kept from freezing by residual heat from Callisto's formation, gravitational energy released when material fell together to form the Moon, not yet fully radiated away, and by heat from radioactive decay of long-lived isotopes like uranium-238 and thorium-238 in the rocky interior, elements that will continue producing heat for billions of years as they slowly decay. Callisto orbits beyond the most intense part of Jupiter's radiation belts, in a region where radiation levels are hundreds of times lower than at Europa, making it potentially a safer destination for future human exploration of the Jupiter system than the inner moons, which are bathed in intense radiation that would be harmful to astronauts and damaging to electronics. A base on Callisto could serve as a hub for studying the Jupiter system, with water ice available for life support and for making rocket fuel through electrolysis, with lower radiation allowing longer surface stays. Time on Callisto is measured entirely in billions. Its surface age is comparable to the solar system itself at 4 billion years or more, its interior cold and sluggish, its future stretching billions of years ahead, barring some catastrophic collision. It exists as a museum, a monument, a world that remembers when the solar system was young and violent, preserving that memory in countless craters. Now we drift outward through space, leaving Jupiter and its moons behind, traveling through the asteroid belt and beyond to Saturn at 1.4 billion kilometers from the Sun, the ringed jewel of the solar system. Saturn is famous for its spectacular ring system extending hundreds of thousands of kilometers, but only tens of meters thick. But it's equally remarkable for its moons, 274 confirmed satellites as of 2025, more than any other planet, making Saturn the true king of moons. These moons range from tiny moonlets embedded in the rings, just tens of meters across, barely distinguishable from large ring particles, to massive Titan larger than Mercury. Some are shepherd moons that help keep ring particles in line through gravitational interactions. Prometheus and Pandora flanking the F-ring, creating waves and kinks through their gravitational perturbations. Some share orbits with larger moons, trapped at Lagrange points, Telesto and Calypso sharing Tethys' orbit, Helene and Polydeuces sharing Dionys' orbit. The diversity is extraordinary. Titan stands unique among all moons in the solar system, the only satellite with a thick atmosphere denser than Earth's. At 5,750 kilometers diameter, it's the second largest moon after Ganymede, and it possesses an atmosphere of 1.5 bars surface pressure, 50% denser than Earth's atmosphere at sea level. The atmosphere is composed primarily of nitrogen like Earth's, but with significant methane that creates remarkable chemistry. Beneath orange photochemical haze, thick enough to completely obscure the surface in visible light, lies a landscape eerily familiar, yet utterly alien. The haze is created by photochemistry. Sunlight in the upper atmosphere breaks apart methane molecules, and the resulting fragments recombine into progressively more complex organic compounds called tholins, molecules with dozens or hundreds of atoms that give Titan its orange color. These compounds are similar to those that may have existed on early Earth before life arose, making Titan a natural laboratory for studying prebiotic chemistry. The tholins drift down through the atmosphere like snow, accumulating on the surface over billions of years, in deposits that may be hundreds of meters deep, a reservoir of organic material that could teach us about the chemical pathways leading to life. At Titan's surface, temperature of -179 degrees Celsius, water ice is as hard as granite, forming the bedrock of mountains and highlands. But liquid methane and ethane flow like water on Earth in a complete hydrological cycle operating at these alien temperatures. Methane evaporates from lakes in warm regions or during summer, rises into the atmosphere where it can be carried thousands of kilometers by winds, condenses into clouds at altitude where temperatures drop, and rains down elsewhere. Methane rain falling through thick atmosphere with droplets twice the size of Earth's raindrops, but falling more slowly through the dense air and low gravity, each drop taking perhaps 10 minutes to fall from high clouds to the surface. The rain carves channels into the ice bedrock, creating river networks that look remarkably like rivers on Earth when viewed from orbit. Dendritic patterns branching and merging, flowing from highlands toward lowlands, collecting into larger channels that eventually empty into lakes and seas. In the northern polar regions, where it's currently summer in Titan's 29.5-year seasonal cycle, mirroring Saturn's 29.5-year orbit, vast seas fill topographic basins. Kraken Mare extends over 400,000 square kilometers, with depths exceeding 100 meters, larger than Lake Superior, a true sea of liquid hydrocarbons fed by methane rivers. Ligeia Mare and Pangamare are smaller but still enormous by terrestrial lake standards. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, used radar to peer through Titan's haze and map these features. Radar bounces off the surface and returns, and by analyzing the reflections, we can determine surface roughness and composition. The seas show smooth radar-dark returns, indicating calm liquid surfaces, while land shows rougher returns. The shorelines are remarkably sharp, with wave-cut features suggesting that waves lap at Titan's beaches, though they're gentle waves in the thick atmosphere and low gravity, perhaps just centimeters high rather than meters. Dunes of organic material stretch across equatorial regions, long parallel dunes hundreds of kilometers long, formed by winds carrying fine particles, similar in morphology to dunes in Earth's deserts, though composed of hydrocarbons rather than silica. Beneath Titan's icy crust lies yet another ocean, this one made of water mixed with ammonia, kept liquid despite freezing temperatures by the antifreeze effect of dissolved ammonia. Evidence for this subsurface ocean comes from measurements of how Titan's shape responds to Saturn's tidal forces during Titan's 16-day orbit. The ice shell floats on this liquid layer like icebergs float on Earth's oceans, and tidal forces squeeze and release the moon, causing measurable changes in shape that reveal the presence of a liquid layer at depth. So Titan is a world of two oceans, one above made of methane and ethane that we can see flowing on the surface, and one below made of water and ammonia hidden beneath kilometers of ice, separated by a shell of ice that may be 50 to 100 kilometers thick. could life exist on Titan? Perhaps not in the familiar sense. The surface is too cold for water-based biochemistry, and the methane lakes lack the chemical complexity that water provides as a solvent. But some scientists speculate about exotic life forms that might use liquid methane instead of water, using acetylene or other hydrocarbons as an energy source, adapted to extreme cold in ways we haven't imagined. Or perhaps life exists in the subsurface water ocean, warmed by tidal heating and chemical energy, isolated from the surface. NASA's Dragonfly mission, a rotorcraft lander scheduled to launch in 2028 and arrive at Titan in the 2030s, will explore Titan's surface directly, flying from site to site, sampling different terrains, analyzing organic chemistry, searching for signs of prebiotic or even biotic processes. Then there's Enceladus, tiny at just 500 kilometers diameter, yet one of the most remarkable and important discoveries in planetary science. At its south pole, geysers erupt continuously from 4 parallel fractures nicknamed tiger stripes because of their appearance in images. Long, dark, warm fractures contrasting with the bright, cold surrounding terrain. These geysers shoot water vapor, ice particles, salts, organic molecules, silica particles, and molecular hydrogen, hundreds of kilometers into space at velocities reaching 400 meters per second. Fast enough to escape Enceladus's weak gravity and feed Saturn's E-ring with fresh material continuously. The discovery of these plumes by Cassini in 2005 was unexpected and transformative. Before Cassini, Enceladus was thought to be a small, cold, dead moon. But the plumes revealed ongoing geological activity and, more importantly, a subsurface ocean that might be habitable. The chemistry of the plumes tells a remarkable story. The water contains salts at concentrations, suggesting an ocean similar to Earth's oceans in salinity. The silica particles indicate water at least 90 degrees Celsius reacting with silicate rocks on the ocean floor, hydrothermal activity. And the molecular hydrogen is particularly tantalizing because it suggests serpentinization reactions where water chemically reduces iron-bearing minerals in the rocky core, a process that on Earth provides energy for chemosynthetic microorganisms at hydrothermal vents. Recent research from 2025 has confirmed that Enceladus's ocean is likely stable over geological time, warmed by tidal heating that generates perhaps 10 to 20 gigawatts continuously, about the same as a dozen large power plants, as Saturn's gravity flexes Enceladus's interior during its 1.37-day orbit. Orbital resonances with other Saturn moons maintain Enceladus's orbital eccentricity, ensuring that tidal heating continues. The ice shell is perhaps 20 to 28 kilometers thick, according to gravity measurements, beneath which lies a global ocean perhaps 10 kilometers deep, directly contacting a rocky seafloor where hydrothermal vents likely exist. Enceladus has become one of the highest priority targets for the search for life because it's so accessible. The geysers eject ocean material into space, where spacecraft can fly through and sample it without needing to drill through ice. Cassini flew through the plumes multiple times, tasting the ocean and analyzing its chemistry. Future missions could carry more sophisticated instruments to search for amino acids, lipids, or other potential biosignatures. Time on Enceladus operates on multiple scales. The geysers vary in intensity with orbital position, strongest at apoapsis, when Enceladus is farthest from Saturn, and tidal forces have released their grips slightly, allowing cracks to open wider. The ocean has likely existed for millions or billions of years, providing stable conditions where life could arise and persist if conditions are right. We could explore Saturn's other moons, Mimas, with its enormous Herschel crater making it look like the Death Star, Tethys with its huge Odysseus crater and mysterious red streaks, Dione with bright ice cliffs, Rhea Saturn's second largest moon possibly with its own tenuous oxygen atmosphere created by radiation breaking apart water molecules, Iapetus with its bizarre two-toned coloration and equatorial ridge, Hyperion tumbling chaotically with its sponge-like appearance. Each has its own story, its own geology, its own place in Saturn's complex system. But time flows forward and we must drift outward. And so we return one final time to our original question, the question that opened this journey. What is a moon? After exploring nearly 900 worlds, after contemplating their diversity and origins, after understanding how they formed and evolved, what answer can we give? A moon is matter existing in space and time, atoms that have existed for billions of years, arranged temporarily into a configuration we recognize as a world. A moon is a companion to a planet, bound by gravity, orbiting for eons, witnessing cosmic history. A moon is a product of formation processes, accretion in circumplanetary disks, capture from wandering orbits, birth from catastrophic collisions. A moon is geology and chemistry, ice and rock, silence and eruption, ancient and young. A moon is possibility, oceans hidden beneath ice where life might swim in eternal darkness. Organic chemistry creating molecules that might one day assemble into something we'd recognize as alive. More than 890 moons orbit through our solar system as we understand it today in 2025, each one unique, each carrying mysteries. Some harbor oceans where twice Earth's water volume lies hidden. Others preserve 4-billion-year-old surfaces recording ancient violence. Some erupt geysers offering samples of subsurface seas. Others rain methane from organic haze. All exist in the great cosmic flow of space and time, following orbits determined billions of years ago, slowly evolving according to physical laws that have operated unchanged since the universe began. As you lie here now, breathing slowly, imagine yourself floating among them one final time, drifting past Europa's fractured ice, thinking of the ocean below, watching Io's fire paint Jupiter's shadow, descending through Titan's orange haze toward methane seas, floating through Enceladus's geysers, tasting an alien ocean. Feel yourself weightless, timeless, part of the same cosmic dance that began 13.8 billion years ago and continues through this present moment. The philosopher Tsiolkovsky wrote that every atom experiences countless lives separated by vast intervals, yet subjectively merging into one continuous existence. The atoms in your body have existed for billions of years, were once part of stars, were scattered in supernova explosions, were gathered into the solar nebula, and will continue existing billions of years hence in other forms. You are stardust, literally, connected to these moons by shared material history, by the fundamental unity of matter and space and time that philosophy and physics reveal. So rest now in this knowledge. Let sleep come like nightfall on a distant moon, quiet, inevitable, gentle. Let time pass unmarked as you rest, flowing forward according to laws we've discovered, but don't fully understand. The moons circle in darkness, illuminated by distant sunlight, or their planets' reflected light, existing whether we observe them or not, following ancient patterns established billions of years ago. Thank you for being here tonight, for sharing this long journey through the moons of our solar system, through space and time, through matter and memory. These worlds, hundreds of them orbiting in darkness billions of kilometers from Earth, will continue their eternal dance long after we're gone. Some may harbor life, proving we're not alone. Others preserve history in ancient craters. All are beautiful, from Io's fury to Europa's ice, from Titan's methane rains to Enceladus's geysers, from Callisto's scars to Triton's backward dance. May your dreams be filled with these distant worlds, with ice and fire, hidden oceans and erupting geysers, methane rivers and ancient craters. May you drift among the moons in your sleep, weightless and free, exploring worlds that exist for themselves, following physical laws whether anyone watches or not. Sleep well, traveler through space and time. Rest among the stars, among the moons, among the countless worlds circling through cosmic darkness. The universe is vast beyond comprehension, and you are part of it, connected to every moon by forces older than Earth, by shared atoms forged in stellar cores, by the fundamental unity of all existence. Close your eyes now if they're not already closed. Let the moons watch over you as they watch over their planets, silent companions in the eternal dance through space-time. Let time pass unmarked as you rest, flowing forward indifferent to observation. The moons were here before us and will remain long after, witnesses to cosmic time far exceeding human timescales, existing in deep time that stretches billions of years into past and future. Good night, dear traveler. Sweet dreams among the moons of our solar system, among the matter that composes them and you, existing together in space and time. May you find peace in the vastness, comfort in the knowledge that we are all made of star stuff, all part of the same cosmic story that began with the Big Bang and continues now through this quiet moment. Sleep now. The universe watches over you, patient and eternal.